Hi everyone and welcome back to physics. This is Mrs. Hutchinson and today we're going to continue our discussion on motion and we're going to really talk a little bit more about graphing motion and the relationships between different types of graphs. So here is a prime example. If we're talking about constant velocity, we have several different types of graphs that can represent constant velocity. It all depends on what their labels are for their axes. So let's think about constant velocity. What does that actually mean? What do we know when we're defining something with constant velocity? Well, for us, that means that you have no acceleration. So let's start off with our easiest graph, acceleration versus time. So over a period of time, if we're moving at constant velocity, our acceleration must always be zero. So our graph would depict that our acceleration is zero for every single time that we're looking at. Now, thinking about constant velocity, what does that mean? What does that mean in terms of our velocity? That means our velocity is actually not changing. So if our velocity isn't changing, that means that we have a constant value. So let's just say, hypothetically, for good measure, we've got our velocity is equal to 5 meters per second. So if we've got our velocity equal to 5 meters per second, it's always going to be 5 meters per second, which means our graph for velocity is going to be a constant straight line. Now, things I want you to think about in terms of constant velocity for position. If you're going 5 meters every second, that means that after 1 second, you've covered 5 meters. After 2 seconds, you've covered 10 meters. 3 seconds, 15 meters. So if we were to graph all of those points, we would get hopefully a straighter line than that, but a nice, straight, direct relationship. Because every second we're covering the same distance. So these are the graphs that can represent constant velocity. And lots of times in physics we ask you to identify, well, which two graphs will represent the motion of a constant moving object, or an object that contains constant velocity. And you would have to pick out the appropriate two graphs. Now again, this isn't something that I want you to memorize, this is something that I want you to understand. Constant velocity means no acceleration, therefore our acceleration always has to be zero. Constant velocity means our velocity is constant, which means our velocity graph has to be a straight line, has to be a constant straight line. And constant velocity means that we are consistently moving the same distance over the same period of time, which gives us a nice direct position versus time relationship. Position versus time, basically if you want to think about it, is like distance. Okay? If this doesn't make sense to you, rewind the video, watch it again. Okay, so now let's move on to a different type of graph. Uniform acceleration. So uniform acceleration. When we say uniform acceleration, we're basically talking about constant acceleration. So what did we just learn about something that is constant? Well, that means that that value is happening over the same amount of time. So constant acceleration means that we have a consistent value for acceleration. So let's just say we're moving 5 meters per second squared. So over the same period of time, for every 1 second, we're increasing our speed by 5 meters per second. Our acceleration is going to remain the same, but that's what that's saying. So think about that in terms of velocity. For every second, we're increasing 5 meters per second. So if we go to our second 2 seconds into this, we're now at 10 meters per second. 3 seconds is now at 15 meters per second. So what's our velocity going to look like? It's going to be a nice direct relationship. Because every second in time, we are now increasing our velocity by 5 meters per second. That's what this is depicting here. Now, things I want you to think about in terms of position. Well, if we are increasing our velocity, think about it in terms of, say, track and field, in terms of sprinting. When that gun goes off, for you to sprint the 100 meters, you are accelerating. As you're accelerating, what happens to the amount of distance that you cover? Does it remain the same, or does it increase over the same period of time? Well, think about this right here. Every second, we're covering more of a distance. 5 meters. Then we're moving to 10 meters in that same second. Then we've now covered 15 meters in that same second. So, our position versus time graph is an exponential graph. And those of you that are taking calculus, you may or may not have gotten into this already, but it actually deals with derivatives and integrals. So our position versus time graph, and if you didn't take calculus, it's okay. We're not taking calculus, but our position versus time graph is x squared. As you move to your velocity versus time, you take the derivative of that. So you'll get 2x. As you move to your acceleration versus time, you'll take the derivative again, and you'll get 2. And as you move in the opposite direction, you'll take the integrals. Okay? So that's how all of these are related mathematically. Now again, being able to identify these does not mean simply memorizing. It means understanding. If you have uniform acceleration, you have constant acceleration, which means your velocity is consistently changing. So it's changing a specific amount every time. If your velocity is changing a specific amount every time, you're going to cover more ground over the same period of time, thus giving you a position versus time graph that is exponential. Again, if this is something that doesn't make any sense to you, pause the video, watch it again. Okay? Because now what we're going to do is take a look at a position versus time graph and try and identify what really is going on for this. So, looking at our line segments. So line segment AB, let's do that one first. The slope. Is it a positive or a negative slope? So basically what I'm asking is what you used to do in geometry, identifying the types of slope. So this line right here. Whoa. There we go. There we go. So A to B. So it is a positive slope because it's going up. So what does that mean in terms of direction of motion? It could mean one of two things. Could mean that you're dealing with forward motion, or it could mean that you're dealing with increasing motion. If I can spell that right. Now, looking at this particular graph, are we dealing with acceleration? Well, it's a position versus time graph. So, we've got two types of position versus time graphs, I should say. We've got our constant velocity, and we've got our constant acceleration. So our position versus time for constant velocity, because we're moving at the specific amount, we're moving a specific distance over the same period of time. So our position versus time graph is a direct relationship. However, for constant acceleration, our position versus time graph is an exponential relationship, because you're now covering more distance over the same period of time. So looking at line segment AB, does it have a curve to it? No. So since it doesn't have a curve to it, that means that we must be dealing with constant velocity for this particular section of graph. So are we accelerating or are we experiencing an acceleration? No. So our acceleration, we would say, would be 0. Average speed. Now I know we haven't really talked about how to analyze this, how to get from one graph to another, like what type of calculations you're going to have to do. But what I want you to do is really take a look at our units here. We've got meters and we've got seconds for our position versus time graph. How are you going to get the units that you will need for average speed, which is meters per second? You actually are going to take the slope. So remember, slope is change in y over change in x. Many people like to say rise over run. I think that that's silly. I think you want to use the actual mathematical term. So y2 minus y1 over x2 minus x1. Okay. So let's do our calculation for our speed here. So we've got 200 meters minus 0 meters over 10 seconds minus 0 seconds. So 200 over 10 is actually going to give us our answer of 20 meters per second. Okay. So far, so good. Let's take a look at the next line segment. Okay. So let's go with B to C, this line segment right here. So what's our slope? Well, are we even sloped at all? No. So we have 0 slope. What does that mean in terms of our position? Well, think about this. So you started, you're here, this is you. You started walking in the forward direction, and you walked 200 meters. Now you're staying at 200 meters. So what does that mean in terms of your position or in terms of your movement? You're just standing. You are simply just standing. Because now you are staying at a position of 200 meters. So, direction of motion, we ain't got none. We don't have any motion whatsoever. We're standing. Since we're standing, can we be accelerating? No. We have 0 acceleration. And our average speed, again, since we're just standing, going to be 0. Again, this is what I want you to think about. Here's where you started. You walked 200 meters, and now you're staying at 200 meters, so you are literally just standing there. That's pretty easy. That's pretty nice. You want to use logic to help you figure this out. For line segments C and D, you start walking back. And you walk back 50 meters. So what is our slope? It's going to be a negative slope. Direction of motion is either backward or decreasing. Okay. Think about it in terms of acceleration. Do you see any part of that line that is curved? Does there have any curve to it whatsoever? No. Since it is a straight line, it's representing constant velocity. Therefore, we're experiencing no acceleration. Our average speed, again, you want to use our slope to help us figure this out. So we will do 200 meters minus 150 meters over 20 seconds minus 25 seconds. So negative 10 meters per second. That would be our average speed. It's negative because we're moving in the opposite direction. Remember, This actually should say average velocity because velocity has direction associated to it. I want you to try the next part on your own. So pause the video, try and do line segment D and E on your own. Okay, so here is how you would do line segment D and E. Hopefully you paused it. So our sign, slope sign, is going to be negative. Our direction of motion is, again, it's either backward or decreasing. Our acceleration, since we have no slope associated with it, it's going to be 0. And our average speed, if you take the slope, you should have gotten negative 7.5 meters per second. Again, here is how we got our direction of motion. Okay. We covered our last 150 meters. Okay, so hopefully that makes a little bit of sense for us. If this doesn't make any sense, make sure that you pause the video, rewind it, watch it again. If it does make sense, let's move on to the next section. Okay, so here is where it kind of deals with a lot of math in this particular instance. So graphical analysis of motion, let me read through all of this, and this actually makes some sense. You have to do dimensional analysis with your units to figure out how you are going to determine something using a particular graph. This is something that takes a lot of practice and a lot of understanding. If you struggle with math, you are going to struggle with this particular section, so make sure that you pay attention. Graphical analysis of motion helps you picture the relationships among position, velocity, and acceleration. If you have a graph of any one of the 3 variables with respect to time, you can find the other 2 by determining the area under the curve or the slope of the curve. If you are taking calculus or have taken pre-calculus, you know about the area under the curve, which is our integral, and you know about the slope of the curve. As you work with the graphs, keep in mind what each axis represents. To derive a position versus time graph from a velocity graph, graph the time versus the area under the curve at that particular time. If you label your axis carefully, dimensional analysis will tell you whether or not you have used the correct relationship. And I'm going to show you what that means. The units of slope, change in y over change in x, will be the y-axis units divided by the x-axis units. So if you're dealing with a velocity versus time graph, so if we've got our velocity versus time graph, here's our units, meters per second. Let's just say, let's just do that type of graph, sure. So if we graph our velocity versus time, and we had to figure out slope. Slope means change in y over change in x. Looking at our units, we would have meters per second over seconds. In other words, we would have meters per second squared. So the slope of a velocity versus time graph actually tells us our acceleration. On the other hand, if we look at our area under the curve, so if we take a look at our area means that you're going to multiply our particular units, whether or not you're taking 1/2 base times height because it's a triangle. So if we did that, it would be 1/2 base times height. But we still are multiplying our units. Or if it's a rectangle or a square, we would do length times width. So that means that we would multiply our units. If we multiply our units together, we get meters per second times seconds. Cross off our seconds, and we're left with our units of meters. So our area under the curve actually gives us our position when you're dealing with a velocity versus time graph. So all of these graphs are related depending upon how you manipulate the units. Things I want you to think about. So let me just show you something. If you've got your position versus time, your velocity versus time, and your acceleration versus time, to get from position versus time to velocity versus time, you're going to take slope. To get from velocity versus time to acceleration versus time, you're going to take the slope. To go the opposite direction, you're going to take area under the curve. To get from velocity to position, you're going to take the area under the curve. Because that's how all of the units will manipulate out. The slope of a position versus time graph winds up being meters per second. Change in y over change in x. The slope of a velocity versus time graph is meters per second squared. Meters per second gives us meters per second squared. The area under the curve of an acceleration versus time graph is going to give us our velocity, because meters per second squared times seconds gives us meters per second. The area of a velocity versus time graph gives us meters, because you multiply them. Meters per second times seconds gives us our meters. So that's how all of these relate. Again, you need to be fairly good at math to understand this concept. If this is something you're struggling with, please make sure that you come and see me sooner rather than later. So now, let's identify the following. The slope of a position versus time graph. What is that going to help us find? That's going to help us find our velocity. Right? Because slope means change in y over change in x. Position versus time. So we've got our meters and our seconds. So we've got meters per second, which would be our unit. The slope of a velocity versus time graph. So meters per second is going to give us meters per second squared. So that's going to give us our acceleration. The area under the curve of our acceleration versus time. So area under the curve of acceleration versus time. If we're undergoing constant acceleration, that means we're finding this. There's our curve. We're finding this area. So that means that we're taking our meters per second squared, and we're going to be multiplying it, because length times width, for area under the curve, or area of a rectangle. So meters per second squared times seconds. That's silly. There we go. Meters per second squared times seconds. Cross off our seconds, and we're left with meters per second, which means we're finding our average velocity. And area under the curve of a velocity versus time graph is going to give us our position, or something known as displacement. Okay. Please, please, please make sure that you understand this. We're going to go over one particular example. Okay. So, moving on. We've got a motorboat travels straight down a river at 40 meters per second. So before we even get into this, what does that even tell us? They tell us our velocity here, but that also tells us for every second we've covered 40 meters. So it says to construct a table showing the total position of the boat at the end of each second for 10 seconds. So starting at 0 seconds, we have gone 0 meters. After 1 second, we've covered 40 meters because 40 meters per second means we've covered 40 meters every second. 2 seconds, 80 meters. 3 seconds, 120. And so on and so forth. So go ahead and fill out the rest of this particular table. Once you've filled out the rest of your table, what I want you to do is go ahead and create an appropriate axis, a scale I should say, for our position versus time graph. So our position goes on our y-axis and our time goes on our x-axis. So go ahead, pause the video, and make an appropriate scale for each one of these using the graph given. Once you've made your appropriate scale, go ahead and graph all of these. So let's go ahead and do that. Okay, so hopefully you got a graph that looks something like this. Not too shabby. I really tried hard on making my lines straight and connecting all the dots and doing whatnot, but there's only so much I can do here. So now part C says to show that the slope of the line is equal to the velocity. So I want you to actually calculate the slope of the line. So we're going to do this up here. So let's do change in y over change in x. Let's pick 2 points on our line. Okay, doesn't matter to me. Let's just pick our first point and our second point. So this one here and this one here. So we would do 80 meters minus 40 meters. 2 seconds minus 1 second. So yes, it's going to be equal to 40 meters per second. Yay! Now, what we want to do on our next graph is actually plot the velocity versus time graph of the boat's motion for the first 10 seconds, and then we're going to find the displacement between the 5th and 10th second. So, let's go to our next slide. And let's find our time and velocity. So, 0 seconds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. Our velocity for each of these, because it's not changing, happens to be 40 meters per second. All the way down. Meters per second. So now, correctly make an axis for this and correctly plot for our velocity versus time graph. So I'm going to pause it and I'm going to create mine. So you should create yours. Hopefully your axes look something like this. What I'm now going to do is plot our velocity here. Since our velocity doesn't change, it's constant, there is our velocity versus time graph. And the question stated, find the displacement between the 5th and 10th seconds. So, displacement between this second, the 5th second, and the 10th second. So displacement for our velocity versus time graph is our area under the curve, because if we take a look at our units here, when we multiply length times width, we're going to get meters per second times seconds. So I'm not exactly sure where I left off, but what I do want to just make sure that I explain, and explain well, is how we determined our displacement. So again, making sure that you understand this, in order to find our displacement for a velocity versus time graph, you do have to find our area under the curve, because looking at these particular units, you have meters per second times seconds. The seconds are going to cancel out, giving us our unit for displacement or position. So for between 5 and 10 seconds, we just have our length and we have our width. So we've got our 40 meters per second for our length. And we've got our 5 seconds here for our time. Multiplying those together, you get 200 meters, which, yes, of course, makes sense, because if you look at the graph prior to this, if you go from 5 seconds to 10 seconds, we started at 200 meters and we ended at 400 meters, so we covered a distance of 200 meters. That's imperative that you understand that. If this is something that you're struggling with, please make sure that you are pausing the video and asking questions as you go. If we take a look at our next question, what I want you to do is pause the video and try question 3 on your own. It is going to be tricky, so please make sure that you take your time with it, review any of this prior video, and I'm going to go over the answers for question 3 in a relatively in-depth manner. So pause the video now and try question 3 on your own. So hopefully you paused the video and you tried question 3. If you struggled with it, that is okay. So first thing we want to notice is what type of graph is this? It's a position versus time graph. Okay, so that makes a big difference. How far does the object travel between 5 and 10 seconds? Okay, how far does it travel? So don't make it any more complex than you have to. So between 5 seconds and 10 seconds, how far did it actually travel? What was our displacement? What was the difference in our positioning? Well, we ended at 20 meters, started at 10 meters, so our object traveled 10 meters. How far does the object travel between 15 and 20 seconds? So we've got here and here, the 2 bigger dots. So we started at 30 meters, we ended at 30 meters, so we traveled 0 meters. We're just simply standing. Our position never changed. During what time interval is the velocity 0? So if our position doesn't change, what does that mean in terms of our movement? Are we moving forward? Are we moving backwards? Or are we just simply standing? Well, if our position isn't changing, that means that we walked 30 meters, we stood still for a while, and then we walked back. So when we're standing still, our velocity is going to be 0. So what time interval are we talking about? We're talking about from here to here. So from 15 to 25 seconds. Our velocity is 0. What is the velocity between 10 and 15 seconds? So velocity. Are we doing area under the curve or are we doing slope? Looking at these particular units, we've got meters, we've got seconds. Our velocity units should be meters per second. So how do we get that? We have to take the slope. So let's go ahead and do that. So for between 10 and 15 seconds, so we've got 30 meters minus 20 meters. Over 15 seconds minus 10 seconds. So if we do that, we get 10 over 5. So we get 2 meters per second. Is the object accelerating during this trip? It's a position versus time graph. So remember, if we're dealing with a position versus time graph and we're dealing with acceleration, there has to be a curve to it. Is there a curve in any portion of this particular graph? No, they're all straight lines. So, it's not accelerating because everything is linear. If I can spell linear. Okay. So now I want you to pause the video and try question number 4 on your own. You're not going to have any homework tonight because it's going to all be incorporated into this video. So pause the video, try question 4. I'm going to go over the answers to question 4 after you hopefully have tried it on your own. So here's question 4. Looking at our graph, first thing we identify, it is a velocity versus time graph. Just make sure you know what type of graph that you are working with. Question states, is the acceleration greater between 2 and 3 seconds or between 5 and 6 seconds? So, things that you want to look at. You could, if you had to determine the acceleration in a velocity versus time graph means that you are dealing with our slope, right? Because acceleration, you're looking for meters per second squared. The only way to get to that would be if we had change in y, which is meters per second. So change in y over change in x. So you look at the slope. You could mathematically determine the slope for this line segment and the slope for this line segment. Or you could just simply look at it and say, well, which one is steeper? If it's steeper, that means that it's covering more ground over the same period of time, or it's moving faster over the same period of time. So, one that has a steeper slope is between 5 and 6 seconds. During what time interval is the acceleration 0? So, I want you to think about this. If we have an acceleration of 0, what does that tell us about our velocity? Is it our velocity changing over time or is it constant? Our acceleration, if it's 0, we must have constant velocity. So, over what time interval do we have constant velocity? Right here. Because our velocity is 10 seconds between 3 and 5 seconds. Our velocity does not change. What is the displacement? Displacement between 5 and 6 seconds. That's where this gets a little tricky. So if we're talking about displacement, what does that mean? Displacement means that we have to take area under the curve, because displacement means that we're dealing with our units of just simply meters. So we have to multiply our units together. But this shape is kind of irregular. So how are we going to go about solving it? Well, we can break it up into 2 shapes. We can break it up into a rectangle, and we can break it up into a triangle. So we're going to solve for the area of both the little triangle and the rectangle. So let's go ahead and let's solve for our area under the curve. So for our triangle, we've got 1/2 base times height. So it's 1/2. Base is 1 second. Height, so 15 minus 10 gives us 5 meters per second. So we would get 2.5 meters for that section, or for that part. And then for our length times width, we would get 10 meters per second times 1 second. So we would get 10 meters. To get our total displacement, we simply add them together. And you should have gotten a displacement of 12.5 meters. So again, with irregularly shaped objects, you just break them up into objects that we know the area of. You know the area formula for. What is the acceleration between 6 and 8 seconds? So again, acceleration, you want to find slope. So acceleration, want to find slope. So we do, if I can get it here we go, change in y over change in x for this particular section here. And you should have gotten -5 meters per second squared. Okay. It's negative because you take a look at the slope itself, it's going down. And what is the displacement between 3 and 4 seconds? Area under the curve. So if you do this, you do length times width, 10 times 1 should give you 10 meters. Okay. If this is something that you struggled with, please make sure that you pause the video, you go back, and you try it again. Okay? Now what I want you to do, if you got these all right, or if you understand it now, I want you to pause the video and try question number 5. I'm going to go over the answers after you pause the video. Taking a look at this particular question, we've got what is the velocity between between 20 and 25 seconds. So we've got position versus time, things you want to take into account. That's what we're looking at. So velocity between 20 and 25 seconds. So we've got this section right here. So it's a position versus time graph. To find our velocity, you have to find our slope. Our slope is not changing, so our velocity is 0 meters per second. Is the velocity greater between 0 and 5 seconds or between 10 and 12 seconds? So taking a look here, we're comparing that to that. So which one gives us the steeper slope? 10 and 12 seconds. What is the velocity between 15 and 20 seconds? So again, we're dealing with slope. So between 15 and 20 seconds is around there. So you want to do change in y over change in x. So taking a look at that, you should get, let's see if I can read it from here. You should get 60 meters minus 51 meters over 20 minus 15. That gives you a value of 1.88 meters per second. Next, what is the velocity at 9 seconds? I'm asking for what is the instantaneous velocity at exactly 9 seconds. So you'll find 9 seconds here, right on the graph. Whoa, that's silly. You'll find exactly 9 seconds. And what is our instantaneous velocity at that point? And you will get 24 meters over 9 seconds. And your instantaneous velocity would be 2.67 meters per second. During what time interval does the object accelerate? So we're dealing with a position versus time graph. If we're dealing with acceleration, our position versus time graph has a curve to it. So they're asking, where is this graph curved, if it's curved at all? So our time interval happens to be between 0 and 12 seconds. And what is the displacement between 15 and 20 seconds? Well, displacement between 15 and 20 seconds. Not too shabby. So you just simply look up 15 seconds, you simply look up 20 seconds, and you take the differences between their displacement. So we've got 60 meters is what we've covered after 20 seconds. After 15 seconds, we've covered 51 meters. So in those 5 seconds, we've covered 9 meters. If you struggled with any of this, please make sure that you watch this video again. I know that it is lengthy, but please, please, please make sure that you watch it again. It is imperative that you understand this material. It comes up quite a bit. So hopefully this made graphing motion a little more clear to you, and I'll see you for our next video.